this is Justin with Casual Conversations, and today we're going to be looking at this kinematics problem from SaveMyExams.com. It's what I use to study for math, so it's a pretty neat website. It does have some paywalls, so be mindful of that, but overall you can use it to get some pretty difficult math questions, and today we have a question about kinematics. It's on the very hard difficulty, but don't worry, I've already done this problem, so I know what to do here, and I'm just gonna do a walkthrough on how to solve a question like this. And this is kind of a question that's really common. Gives you a formula, tells you what to find, and then you go ahead and find it. So first things first, we have a formula given to us here. I'm not really gonna go into the specifics with the question, but always what you want to do when you see a formula and it's a kinematics problem, which you can tell because you're using velocity or acceleration or position, every single time you just want to go ahead and type that in first thing. So, oh, that's not x, but there you go. Type it in, and I'm replacing t with x. That's what you usually do. Every time t is just time, but we're just making that x for all our purposes. So let me type this in 1 second. So I am using a online TI-84 calculator, which is right here. I'll put in the description of the video if you want, but it's kind of obvious, TI-84calc.com. It's pretty good software, and it's pretty accurate to what your calculator is going to be like on the exam. Depends on your school, obviously, but this is pretty much what it's going to look like. Right now I'm just typing it in. What you want to do before you graph it, because some equations take actually like a good chunk of time to graph, you want to set your window first. So for this problem, it already gives us a window here, 0 to 10. So let's have that 0 to 10 for x, and usually for y it doesn't give you anything, but you can tinker around with it. Try to go high and then go lower. But for this problem, it's gonna be about -20 and then positive 75. I think I remember being 75. So yeah. This is the window. You should probably already know this. So yeah, graph it out, you get this. So that is our velocity over time. It's always important to remember what kind of graph you're using here, because if you're using position, it means something completely different, and you're going to be doing different things. But here we have velocity. So it's asking us the first value of t at which p changes its direction of motion. So when it's saying that, it's asking for when this graph goes in another direction. So it starts off going up. You can't really tell, but it starts off going up, then it goes down. So we want to find when it starts going down, because that's when it changes its direction of motion. Sorry, I just got that completely wrong. Ignore what I said for the past 20 seconds. This is a velocity graph, not a position graph. So in the case of a velocity graph, when it's asking for a change in direction of motion, it's when it crosses the x-axis, not when it changes this way. So we want to make sure we're getting the x-axis, the first one, because there's one right here, and we're going to need this one later too, but this one is more important right now. So second calc, you hit, you can do 0, or you can actually just trace it. I'm going to do 0. Left bound, make sure you're on the left side of what you're trying to find. Then let's get our right bound. Boom, bam, 2. So this is, write this down, 6a, 2. And when you're actually writing it on your exam booklet, I'm not quite sure. I think you're supposed to sketch out the graph. So you would draw something similar to this, and then boom, put 2 there. And if you're unsure about whether this was increasing or not, you can always do zoom and do z-box, and obviously box in where you want to check out, and then you'll be able to tell much easier whether or not it's going up or down, or where it's crossing the x-axis. I was only doing it without the zoom because I already did this problem, obviously. So yeah, we have 6a done. Let's move on to 6b. So find the total distance traveled by p during the periods when its speed is increasing. Okay, this one's kind of tricky, and I'll tell you why. It's because of this part where it says during the periods when its speed is increasing. What does that mean? It means its speed is getting higher in magnitude. That's the best way I can put it, which means the number is getting higher. Now, throughout this whole thing, you can see it's either getting closer or further away from the x-axis. We want every single period where it's getting further from the x-axis. So, for example, right here it's getting closer to the x-axis. We don't want that. But once it crosses it, now it's going further away. You see that? So we're trying to get every single range that it's going away from the x-axis. So to do that, we need to find this point, and this point that I'm at right now. Because always a general good idea to find your maximums, your minimums, and your x-axis interceptions, because those are usually what you're going to be using. You might not use all of them, but it's always a good idea to make sure you know them all. So I'm just going to quickly do second min on this point that I'm at right now. This is how you find the minimum. And we get 4.64 roughly. Yep. Then we're going to do our second calc. Second calc maximum to get that really tall point on the right there. Boom, bam. We get 8.37 or 8.38. Write that down. I already have it written down, so I'm not actually writing anything, but just for, your purposes. And then we're going to go second calc to find that really tiny maximum that's on the very left side here. You can't really tell on this bigger, zoom out, but when you do the zoom in, you'll see that there is actually a local maximum right there. And you get 1.37. So we got all our maximums, all our minimums that are in the range. Now we need to find our intercepts. So second calc 0. We already found the other one, which was 2. So we can just quickly find this one. Left bound, right bound. Actually zoom in a little bit for everyone. Right, you can see that it's at 6. So we have 2, 6, and then we have our maximum of 1.3 whatever, 4.6 whatever, and then 8.38. Okay, so we have all of our points that we need. Now, how do we use them? We're going to do the integral, because as we know, integrals are what you use to find distance when you have the velocity graph. Only for the velocity graph, because if you have any other type of graph, your integral is going to be something different. For position, your integral is like, I don't even know if it has a really practical application, so ignore that. But for the acceleration, your integral is the amount of velocity that changes over time. So if you want to know what that is. So if a question asked you, what's the total velocity change in a certain period, that's when you'd use the integral on an acceleration graph. But here we have a velocity graph, and it's asking us for distance traveled. So we have to use the integral. How do we use the integral? So when you're going to second quit, math 9 is how you get the actual integral function. This is a definite integral, by the way. The bottom is going to be the leftmost point that you're trying to find, and then the rightmost point. So left and right boundaries, just like how you do the calculations on the graph. So you want to put your leftmost point and your rightmost point, and within that boundary, it's going to find the area under the curve, or the area to the x-axis. So back to the graph. Where exactly do we need to do this? It's going to be, and it's kind of hard to do this on the graphing calculator. It's hard to visualize all this. So I understand if it's kind of choppy, but we want every single range that it's going away from the x-axis. So from this point, which we already said was the 8 point whatever, to the 6, it's going away from the x-axis. You can see it's going away. It's getting larger in magnitude. Then it starts going back down. So this range is going to be counted here from the minimum of the graph to the x-axis. It's actually decreasing because it's getting closer. I know it's going the same direction as this one, but it's getting closer to this axis. So we're not going to count this range from the minimum to the x-axis here. However, the minimum back to the other x-axis point is going away from the x-axis, so we're going to count that. And if you do zoom in, well, I'll zoom in. Okay, so if we zoom in here, we see that it's really slightly going away from the x-axis. You can't really tell on the bigger graph, but it is going away from the x-axis. So we're going to count 0, which is here, to our maximum here, which we already said was 1.37. And I know it's kind of hard to keep track of all these crazy numbers when I'm not writing it down on the screen, but hopefully this is making a bit of sense to everybody. Maybe in future episodes I'll actually write my stuff out better. But let me reset the window really quickly so it looks normal. Okay, so back to the normal graph. We're going to count this range to like this little maximum here. Then we're going to count this, or sorry, the x-intercept to this minimum, and then here to here. Okay, so now we have to actually do it. Now this is going to be the most difficult part. Not difficult, more like tedious. You have to make sure that you're doing your absolute value bars correctly, because if you look at the graph, when it's under here, we don't want to count negative area because that doesn't really make sense, and that would also violate the fact that distance is not a vector value. It's a vector quantity. It's a scalar. So if it was asking for displacement, then it'd be a different story. We wouldn't use absolute value bars. But since it's saying distance, that means it wants a scalar, which means no signs on it, which means we don't want to count this as negative area, subtracting it from here. That wouldn't make sense, So we're going to make sure we have absolute value bars. You can do it for every single one, but you don't really have to because the positive ones won't turn negative. So yeah, we're going to do 0 to 1.37. So let's go ahead and do 0 to 1.37. Okay, so here we have our integral. Notice I did not put the absolute value bars on this one because this is over the x-axis. Obviously you can't tell because I'm not zoomed in, but it is above the x-axis, so we're not going to put any absolute value bars on it. You can always just be safe and put them on anyways. Up to you. So now we're going to do 2, which is right here, to our minimum, because that is going away from the x-axis. So 2 to our minimum, which we already said was 4.64. Okay, so let's go ahead and do that. Okay, so we finished the integral for this one, and that is, that's not, I have second on, sorry. So, and that was from here to here. So that's calculating that area. We have absolute value bars, so we make sure we're not subtracting it instead of adding it because of that distance being a scalar quantity. Okay, so now we have here to here. We're not going to count here to here because that is going toward the x-axis. So we're going to count from this x-intercept to this maximum, and that will be our last integral. So it's going to be 6 to 8.38. Those will be our last ones. Let's go ahead and do that integral. Okay, so we finished that integral, and a reminder that there's no absolute value bars in this one because we are already in the positive, area. We only put the absolute value bars in this one, which was our second integral that we did. So now we're going to go ahead and calculate all this, and it might take a little second. That's expected. Don't worry about it. Oh, it was pretty fast. 118.699 is our answer for B. So now we're going to do the final part of this question. This seems like to be one of those last questions on the first section of the paper one. Or sorry, paper 2, obviously this is calculator. But, paper 2 is split up into section A and B, with B being much longer questions, usually getting to like the D to F range almost. As in like 6A, B, C, and so on. This one only goes up to C, so it's probably at like the end of section 1. So this is one that you want to kind of get through fast, and it's kind of hard because of how long it takes to write out these integrals. But trust me, when you have the actual handheld calculator, it's much faster. Okay, so a second particle Q also moves along a straight line. Its velocity after whatever seconds is given by that equation, and it has that window. Okay, so this is more like I like to call these SAT questions. And what I mean by that is SAT loves to spam a bunch of variables, throwing in unknowns into your question. And that's what IB kind of likes to do too. So here they've put in a K, after K seconds, the total distance that Q has traveled is the same as the distance that P travels during its periods of increasing speed. Okay, so what is this question asking? It's asking, what values we'd have to put in for x in order to get the same thing that we just got here. So it has to equal 118. Now the way I like to do these is first understand what's going on, and that's kind of what I just did. You know, we have to make the integral of this equal 118, essentially, because the integral is the distance, so it's saying the same distance, and if we do the integral of this function from one place to another, then we'll know, okay? Does that make sense? I'm not quite sure if I'm explaining it well, but maybe if I just go ahead and work through it, it'll be a little easier. So I can't really write out anything because I don't have a stylus or anything like that. So I'll tell you guys what this integral is, and if you don't remember how to do an integral, put it in the comments and I can help, make a really long video about that, but I'm going to glaze over that for now. We do the integral of this function. Obviously there's a plus c at the end, but we're going to do a definite integral, so we're not going to actually put that plus c. So the 6t squared divide 2, and then that gives you 3t squared plus 2t as your integral. So if we put that in here, delete this, we're not going to need it anymore. Let's do 3x squared. Remember, we're replacing t with x plus 2x. That's our integral right there. Let's see what this graph looks like. Okay, this is pretty beneficial because we're not going below the x-axis at all. It's just a straight line, well, straight as an exponential can be, but it's not going down, it's not having curves like that, right? And actually, I'm going to zoom in like a bunch here to really get this through, because I know my quality is pretty bad. I'm sorry about that, guys. I don't really know how to fix that, but yeah. We have our integral. This is the integral function, not this function. It's the integral of that function. Alright, cut in from future me. I made a mistake when I was explaining this concept originally. So there's just a big cut in the video. You're going to see me just pop up with the, y1 equals this, y2 equals this screen. The bottom one is going to be 118, which is the answers to our previous problem. And essentially what we're trying to do was find the value of k so that the derivative of another function equaled the same, or sorry, not the derivative, the integral of another function equaled the same of another one. And the reason I explained it poorly was because I was explaining it as another area under the curve problem. I was saying how far do we need to go out this way in order to get an area of 118. So how far we need to go out here, which would be k, to get an area under the curve of 118. However, that was wrong because that was under the assumption that it was a velocity graph, but that's not the case. It was already plotting the integral. Does that make sense? If it was already plotting the integral, then we just need to find the intercept, and that's what we do in the video, but I explained it a little poorly, and you'll see me have that whole realization and, kind of retroactively correct what I did, but I just wanted to put in a little note here so that you guys understand what happened there. As a reminder, when you're going from position to velocity to acceleration, it's going downwards that you do the derivative. That's kind of how I remember it. And then going upwards, you do the integral. Kind of a weird way to remember it, but yeah, that's the general concept that I kind of forgot here. And I ended up doing the wrong thing, but I did it in the right way. Or maybe the other way around, I don't know, but I got a little confused. General picture is make sure you're using the right graphs, because I obviously did not do that. But I correct myself, and we get the right answer in the end, so just bear with me here. Alright, thank you. That was really a ramble, I'm sorry, but let's get to the point. You want to find the intersection of these. Since the y value is so high, just set the y value on the window to be higher. Do 100 to 120, and boom, there's the intersection, second intersect. And you'd want to write this out in some way that the grader could tell what you're doing, in case you do mess something up. You can get some partial credit, but there you go, 5.965. That's our answer. So if you think about it, what this is basically saying Okay, wait. I think I had a misinterpretation. So sorry. Looks like I don't really know how to do this problem either. But what I think I messed up on was explaining this. So what I think I messed up in doing is that I explained it as how far we have to go out here to get the area of 118. However, that's not correct, because this is the integral. The value that you get from it is the area. It's how far we have to go out and then go up there. How far does this have to go out for the y value to be 118, not the area, just the y value, because this is already the integral. That interpretation is if this was the actual function. So if we were to put, for example, now this black line would be how far we have to go out to get that area. But this blue line, being our integral, is already that value. So we just have to find the intersection, which is what we did, and we got that 5.8 or whatever number it was. So does that make sense? I hope that makes sense to all you guys watching. So yeah, let's check our answers real quick. 2, like we said, this was 118 point something. Yep. They rounded it to 3 sig figs. So I think that's kind of standard for IB. Make sure you're rounding this 3 sig figs if you don't know how to round, or unless it states otherwise. And then finally, 5.95. They rounded it to 5.95, 3 sig figs. Yeah. So you see they did the same thing here. It's kind of easier to tell. I don't know if you guys can see that very well. Alright, so here it is. We have the solution to the last part of that question. And here's the integral. This is just how they notate it. You see k to 0. Make sure that you're doing the bottom as the left boundary. I don't know why I drew that. Left boundary, right boundary. Then you subtract the top from the bottom when you're doing it by hand. But since we're doing calculators, we usually don't do that. Here is just saying from here to here, this function has to equal that, right? And that's basically what we said. But since this is 0, we can just plug in this and into y1, that into y2, and find the intersection, like they did here. That's only because this is 0. If it wasn't 0, then we'd have to do something different. If it was a value, we just plug it in, find that value, and then subtract it from this function right here. But since it's 0, nothing's at the end, we can just set it equal to each other and then find the intersection. So that's exactly what we did. Boom, bam. It's up there somewhere. And yeah, that's about it. But yeah, that's going to conclude our episode. If you liked it, please leave a like and subscribe. And yes, I'm doing the same thing from the last episode. I'm just putting a bunch of stuff on this little sketch pad. Make sure you're using a TI-84 calculator for studying. And then the main takeaways from this episode are kinematics and how they can be cheesed almost essentially every time, as long as you're understanding what graph you're using. You don't get mixed up like I did multiple times here. And you're making sure that you're using the right notation in your calculator, because if you do not use absolute value bars, for instance, then you might be getting the wrong answer. So main takeaway is just make sure you're using your calculator correctly, make sure you're using the right graphs, and make sure your understanding of kinematics and its fundamental principles are a-okay. If you guys want a video on the basics of kinematics, just let me know. But yeah, that's about it.